To wrap up this unit, we're going to look at how we can create models of real-life events using logarithms and exponential equations. So we're going to look at this first one. It says in 1970, and this is true, these are true data, in 1970 the minimum wage was $1.60 per hour. In the year 2000 it was $5.15 per hour. Use this information to find a model of the form a equals a naught e to the kt. So just a reminder that a naught is one single variable. Okay, that is one thing. If they'd just written a there, it'd be the same thing. Or if they'd written p, it represents our initial amount. Okay, now it says we want to make a model. We may say, well, there's already an equation there. Well, the equation is incomplete. E is a number, so that's fine. And then a, the a out front here, and t right here are our variables. So we don't need a number for them because we want to be able to plug things into those. So a and t are fine. E is fine because it's already a number. But a naught and k are two constants that we need to find out. So again, a is your variable just like y. It's equivalent to the y. T is your variable. It's equivalent to x. You don't need to solve for those because that's what you want to have an equation. You want a y and an x, or in this case an a and a t. But you need to know the constants. So let me show you one thing that may help you understand where I'm coming from. You're probably very familiar with y equals mx plus b. That's the general form for a straight line. Well, we need more than that if we're actually going to draw the line. We need our slope and we need our y-intercept because these are our constants that we don't know. Y and x, we'll just leave y and x because they're our variables. So you could have something like y equals 3x plus 4. Now that equation is complete. Now it's usable and we can graph that or do whatever we need to do with it. So you have to find the constants of an equation in order to complete it. Again, you don't have to find the variables. So for the straight line, you don't need y and x. Just like in the one we're about to work on, you don't need a and you don't need t. You need the constants, which would be a naught and k. So let's go back and look at what they tell us. It starts in 1970, and it says that the minimum wage in that year was $1.60 per hour. Okay, well 1970 is apparently our starting point then, because we don't have any earlier information, so we'll treat 1970 as the starting point. And our initial amount then was $1.60. So according to this, I'm going to say that is a naught. So I can at least update my equation now and write a equals $1.60 e to the kt. Now we need to use the other pieces of information we're given in order to solve for the k. So we know in 1970, that's our starting point. We had $1.60 an hour as the minimum wage. And then it says in 2000, so that's 30 years later. So what I'm going to do is plug in 30 for my time. 30 years later, it was $5.15 an hour. So I need to plug in $5.15 as the minimum wage in 2000, which is 30 years after our starting point. So if you notice, now I have everything but k, so I can solve for k. So I divide both sides by $1.60. That gives me 3.21875. I need to get rid of the e, so I take the natural log of both sides. So I get the natural log of 3.21875 equals k times 30, because remember, the natural log cancels out the e, so we can just get rid of it when we do the natural log of both sides. The last step then is just divide by 30. So when I do that, I get something like 0.03897. It's a good idea on these to use at least 3 or 4 decimal places just to keep things more accurate. So I would at least want you to go 3 decimal places, so we'd go 0.039 perhaps. Let me show you one thing you can do in the calculator that you may not have known if you're trying to save a really long number. Okay, so my last step here was that I took the natural log of 3.21875, then I divided by 30. Okay, now you may need to use that number later, and you maybe would rather not round it. Maybe you want to make sure you have the exact correct number. Well, you can actually save this number in your calculator. If you click Store, which is just above On, and then you can pick any letter you want. So you have to click alpha up here, and then you can pick any letter. I usually just pick A because it's easy. You hit enter. So what that's done is that has now saved that number as A. Or actually, since we're calling it K, we could just store it as K. Let's do that. So store alpha K. So now anytime I type K, just say alpha K, that number comes back up for me. So that way I don't have to write the whole thing down on my paper, but it's stored in the calculator, and if I need to use it later on in the problem or for a different problem or something like that, it's there for me. And anytime you store something, it just overwrites. So if the next problem has a different K, you can just do store alpha K, and that new one will take that old one's place. So that's a good way to save a long number without having to just write it down all the time. Alright, but that's not quite our final answer, because again, our final answer is going to have A and T, because we want the equation. We want to know what the equation will look like. So we need to plug in A naught, which we said is $1.60, because that is our initial amount. We need to plug in our K, which I'll just say is 0.039, times T. So this is the equation they want you to write. You've got to plug in your constants, which are A naught and K. And that model will now give you an estimate for the minimum wage. So you can estimate, okay, what would we expect the minimum wage to be in 2010 based on this model? What would we expect the minimum wage to be in 2020 or 2030 or 2050? So this, using old data here, allows us to give an estimate or a way to guess what it will be in the future. Okay, next one. Find the exponential model for A equals A naught e to the kt for carbon-14, which has a half-life of 5,715 years. Alright, so this one takes a little more creativity because it doesn't give quite as much information, or at least not in the same way as the previous one. If you notice, it doesn't come out and tell you what the initial amount is. Well, here's the way I would look at it. When something starts, it has all of its carbon. So I would just call that 100%. So I'm going to call A naught 100, meaning 100%, because it starts with all of it. Okay, I don't know K, I don't know my rate, but I am told a time. I'm told 5,715 years. So let's talk about what that 5,715 years means. It says it's its half-life. And if you're not familiar with this, you haven't studied this in chemistry or earth science or anything like that, the idea behind a half-life is that that's the amount of time it takes for half of the material to decay or to dissipate. So that means after 5,715 years, the carbon-14 will be only 50% of what it was. It will be half of what it was. So I'm going to put 50 in for A naught. Excuse me, for A. Because we're going for the same thing here. We've got to solve for A naught and K so we can actually write our equation like it should be. So now we'll divide both sides by 100. Gives me 1/2 equals e to the k times 5715. I can take the natural log of both sides. I get the natural log of 1/2 equals k times 5715. And then divide both sides by 5715. So let's see what that gives us. Natural log of 1/2 divided by 5715. Okay, and we get a very tiny number. So this is again where it would be helpful to just store this number. So I'm just going to store it as alpha k. So I can use that later, because we're talking about something that's like 0.0001. So on my paper, that's probably the best I can do is just write, okay, k is equal to 0.000121, I think is what it was. Yeah, we'll go with that. Okay, so when we write our equation, we would have A equals, and then you can put 100 here, you can leave this, let's just put 100, we'll stick with that because it's 100%, e to the k, which is 0.000121 times your time. So that will tell you after a certain number of years what percent of the carbon-14 would be left. Now let's look at this example they give below. It says the Dead Sea Scrolls. If you're not familiar with those, there are some documents that were found, I think in the early 1900s, that are actually very old copies of Scripture. So they're old copies of the Bible, basically, or at least of the letters and the books that make up the Bible, that they were found in a cave in the early 1900s. So the Dead Sea Scrolls were found to have 76% of their carbon. Estimate their age using your model. Okay, so we know that the amount left was 76%. So I will plug in 76 for A and solve for the time. I'll divide both sides by 100. So that's just going to give me 0.76 equals e to the 0.0012. Oh, I'm forgetting a 0. There's one extra 0 there. There we go. Now I can take the natural log of both sides. And divide both sides by 0.000121. Okay, remember, I stored that actual number because that 0.000121 is just an estimate, but I stored the real thing right here. So what I'm going to do is say natural log of 0.76, and then I'm going to divide by the number that I stored in for k. So I'm using the exact number instead of just the estimate. So just type alpha k, that way you don't have to retype that whole number, and hit enter. And you get 222.63. So that's obviously just an estimate, but you know it's somewhere in the neighborhood of 2,000 years old. Okay, the last thing we're going to do is learn to do some of these models in our calculator using regression. So let's look at this particular one. We will plug this in our calculator, and then we're going to decide, because our calculator has both the exponential regression and a logarithmic regression, we're going to decide which one would make the most sense. So what we're going to do is take these data points, these 5 data points, and we're going to plug them in our calculator. Now I've already done that, so you can see they're here in my stat plot, 5.5, 14, 71, and so on. And I have the y values in the L2 plot. Okay, so what I want to do first is see what the shape of the data looks like to decide if log or exponential would make more sense. So what I would do is go to your y equals and clear out any of these you have, and then go up to plot 1 and turn it on. That way it'll actually graph your data points for you. Then you go to zoom, you go all the way down to, I think it's zoom 9, let's see. Yep, zoom 9 is zoom stat. So you hit enter, and that will automatically format your window for you. Okay, so we have to ask ourselves, does this look more like a logarithmic regression or more like a exponential regression? Well, let's just do both in case you're not sure. It should be obvious if you know what those two graphs look like, which one it looks more like, but if you don't know, then let's try it. So let's just go to stat, and we'll scroll down. Let's see what we got here. Okay, so we've got the natural log regression. We'll just go ahead and try that one. And remember, if you use vars and then yvars, hit enter a couple times, then that will plug in the graph for you. Alright, so remember, r squared and r can give you a good idea of how well this thing is fitting. We get an r squared of 0.99. That's awesome, because we want something close to 1, and that is really close to 1. So it looks like natural log is what we want to use. And if you look down here at the graph, clearly that seems to fit the data pretty well. Just so we get the comparison, let's go to stat and do the exponential regression and compare that. So if we try the exponential regression, we'll graph it as well. Okay, see here, r squared is 0.70. That's not very good. We're looking for something close to 1. That's not going to do it for us. If you look at this graph, that's clearly nothing like the shape of the data. This data is not exponentially shaped. So just as a quick reminder, an exponential is going to be shaped like this. It's going to start slow and then move up very quickly. A log is going to do the opposite. It's going to start by moving up very quickly and then slow down. So if you look at the graph that we just had, those data points, you're looking at this graph, the points that is, they start moving up very quickly but then slow down. So that's how we know it's a log. Okay, now let's look at this one as well. Actually, before I do that, let's go back and let's record what this one would look like. Let's pull up again the log regression. Remember, it's going to be ln. There we go. So I would record that as 2.73 plus 0.35 natural log of x. 2.73 plus 0.35 natural log of x. Just make sure you remember how to plug those in and actually write out the equation. Okay, so now we have a new set of data that we will need to plug into our stat plot. So you can see here that I have already plugged it in. I have all the data, 1 through 52, and then 2.6 through 6.2. So let's see. You can see the graph down here, so I'll just look at it here. It looks like this is starting to bend up and go a little faster, but it's not real clear, so we'll try both again, just see how they match up. So we'll try linear regression. Oh, that's the wrong one, sorry. I believe it's 9. There we go. 9 is the natural log regression. So we'll use the var so it'll graph it for us. Okay, that's not a good sign. Our r squared is 0.69. We want something close to 1. That's not so good. And you look at the shape of that, that probably helps you see just how much that's not shaped like natural log. So that's no good. Let's try the exponential instead. So go to Stat, Calc, I believe it's 0, Exponential Regression. We do vars, yvars, and this will graph this for us. Okay, again, much better shape. We have a 0.99, so that's really close to 1. That tells us this is a good fit, and you can tell this follows the flow of the data a lot better. So this one would be written as 2.57 times 1.01 or 1.02 to the x.